Welcome to this video on Claude Code Dynamic Workflows, where we demystify Opus 4.8's complexity ladder, hidden engines, and session gating. Dynamic workflows are often confused with skills, subagents, or the /goal command, but we will clarify when to use each mechanism and how to protect session boundaries. Let's explore the complexity ladder. Static orchestrations like skills and subagents are rigid, human-coded scripts. Level 1 complexity. Dynamic workflows in Opus 4.8 are self-assembling engines. Level 5, capable of fully autonomous execution, including designing, compiling, and testing modular code blocks dynamically. When selecting the right tool, custom skills are best for deterministic scripts and repetitive setups with minimal token risk. Dynamic workflows should be reserved for complex, non-linear dependencies across directories, due to the extremely high and recursive token risk. The /goal feature acts as the planner, interpreting multi-phase objectives. The dynamic workflow is the actual execution engine, constructing runtime blocks and auto-compiling code. They work together but exist at different structural layers. Dynamic workflows feature no predefined graph. Opus 4.8 generates and compiles editors on demand, resolving errors instantly. It uses transient worker workspaces, which are short-lived sandboxes to isolate parallel compiler operations and prevent Git collisions. Ultracode mode is Claude Code's performance throttle. It uses multi-thread AST execution, bypassing shell prompts for optimized raw API calls, and offers gated self-healing, executing commits only when compiler checks report 100% safety. Deep Research integration connects Claude Code to external documentation, scraping live APIs, and querying package registries. This is powerful for fixing package updates, but the constant web scraping and external document parsing are major token consumers. The performance trade-off shows that combining Deep Research with ultracode modes can result in an 8.2x speedup compared to the standard subagent loop. However, this phenomenal speed requires active token and cost monitoring due to increased token burn. In a burn session, 80% of the token budget is consumed by runaway Deep Research scraping loops and recursive compilation failures. Launching a dynamic workflow on a broken external repository without limits can quickly drain your token budget. The dynamic workflow lifecycle includes 4 phases. It starts with a context audit, followed by sandbox isolation. The third phase is swarm assembly, where real-time self-healing runs programmatically. Finally, gated convergence merges changes back with full checks. To protect against session costs, use strict token gatekeepers for human approval before Deep Research queries. Implement local pre-flight checks to verify syntax and lint rules first. Finally, optimized prompt caching keeps files structured, preventing the compiler from reading the entire directory tree repeatedly. We have covered how to safely configure local workspace rules to govern Opus 4.8's dynamic loops. For more information, please check out the resources listed here.